So it's my great pleasure to introduce Zhendong as our second keynote speaker. Zhendong is a good friend of mine, at least as of this morning. I think you won the award because I invited you, right? No, I was done independently. So Zhendong is a professor, Department of Computer Science at ETH Zurich. He's passionate about fundamental and practical innovation for building software. His research spans programming language, compiler, software engineering, computer security, deep learning, education technologies. He's a member of Academia Europaea, a fellow of ACM and IEEE, and participates in the ACM Distinguished Speaker Program. And without further ado, please, Zhendong.
So thanks for the very nice introduction, Charles, and also thanks for the invitation to be here. And also was a very nice, sweet surprise to us that we received this most influential paper award from Uppsala. We were very happy and grateful for the recognition from the community. So I look forward to many engaging deep discussions with colleagues, friends, old and new at SPLASH'. And as the title suggests, I'll focus on compilers in this talk. In fact, I'll argue that there's nothing more exciting than compilers. My hope is to take us on a short journey of reflection and imagination by sharing some personal perspectives. In particular, let's rethink how to build much better compilers. To do so, let's think how to build that perfect compiler. Let's first take a step back, reflect a bit on the past, and then try to reimagine the future. As any discipline, it will be useful to reflect on its core mission. So let's start with this question. What is the key mission of computer science? Each of us may have our different answers. To me, the answer is to help people turn their creative ideas into working systems. And we want to do it well with low cost. In particular, we wish to have a magic ball. We speak to the magic ball about our exciting creative ideas. It produces the perfect working software for us. Software science is about building that magic ball. Indeed, software research and development is central to this mission. As a community, we have made a lot of exciting progress over the past decades. So our general field, software science, namely programming languages and software engineering, has been at the core of computer science. So we should be proud and try to keep it relevant and at the core. Toward this goal, I believe the high-level key mission of our general field is to advance and reimagine the science and practice of software construction. Science to cure our scientific curiosities, practice to have significant real impact. Now let's reflect and imagine about building software to see how things are going. Despite the great progress, the perhaps sad fact is that when one closely examines any software, bugs are common. This figure shows new and accumulative publicly disclosed vulnerabilities from 1988 to 2020 over a more than 30-year span. It could be interesting to contemplate on the many ways to read this figure, but clearly we have a very long way from having reliable and secure software and systems. What can we do? It is clear that building high-quality software needs solid software foundations. If these foundations are buggy, any software built based on them will also be buggy and cannot be relied upon. What are these foundations? Languages and compilers, which are dear to our hearts here, databases, operating systems, and so on. We have, for example, compilers like GCC, LLVM, Rust-C, and so on, databases like SQLite, MySQL, Postgres, and etc. Let's focus on languages and compilers. and I'll focus on compilers. And as good languages have to rely on good compilers. Indeed, I argue compilers are the most important technologies. Just imagine a world where compiler optimizations are turned off. Everything will just halt. We'll ponder how to build good compilers. Good compilers need to generate correct and performant code. In fact, this tension between correctness and performance underlies all of computer science, and particularly for building good software. Building only correct software compilers is straightforward. Building only performant compilers is also trivial. But building both correct and performant compilers is a long-standing grand challenge and an enduring topic for us. So, what is the job of a compiler? It is a translator. It translates source programs to binary executables. For example, from C or Rust to x86. It's also an optimizer. It aims to generate code of high quality. Let's look at it under the hood. A compiler applies multiple transformations. We call them passes throughout the optimization process. These passes are informed by analysis which aim to determine the semantics of the compiled program. This is necessary, for example, to determine whether it's legal to apply a transformation. A compiler also uses heuristics to decide if and how certain transformations should be applied and whether they are profitable. All these components interact with each other with the goal of producing high quality code. We would all love to have a perfect compiler, one that generates correct and best performing code. The community has invested decades, in fact, getting close to not too far from 100 years of efforts to build more and more advanced compilers. Compilers are certainly getting increasingly more feature-rich and more advanced and of significant complexity. But do they get close to that perfect compiler? Now, let's take a step back and reflect on getting to this moonshot ambition. In general, most good research is similar to building taller and taller buildings. That is incremental but solid work by adding new bricks. But can this really help us get us to the moon? The moon for us is that perfect compiler. The answer would be a clear no. But then, how do we may be able to reach our moon? Let's think different. Many of us may have seen Hamming's essay on you and your research, and this particular soul-searching question he asked. What may be our answers to Hamming? What might be our individual scientific and technological moonshots? Next, let's ponder and discuss. One of my answers to Hamming's question would be the pursuit for that perfect optimizing compiler. Recall that we discussed this tension between correctness and performance. Certainly, both need to be tackled. As we know, production compilers are very complex. These numbers were from 2019, a few years ago. Now, all of these have grown a lot bigger. For example, Linux has more than 30 million lines of code, and GCC is getting very close. Thus, definitely a seemingly impossible pursuit to go after a perfect compiler. First, regarding correctness, in fact, we know quite a lot and made much progress, especially in the last decade or so. I'll only talk about briefly. Here is a concrete compiler bug in Clan LLVM, which we'll look at in more detail later. It is a correctness bug called a miscompilation or wrong code bug in compilers. These are the type of bugs we certainly don't want our compilers to have. We have techniques for compiler testing, such as CSmith and EMI. We have translation validation tools like Alive2. And certainly, we also have Concert as a realistic, formally verified compiler end-to-end. These are all essential and influential efforts that advance compiler correctness. Let me briefly highlight EMI, as that's work from my research group. So the problem it tackles is how to find miscompilations in real compilers like GCC and LLVM. It's a daunting task as they are extremely complex. Let's see how we may make a breakthrough. Let's focus on the notion of program equivalence. Here is a classical standard notion. Two programs, P and Q, are equivalent if they yield the same result on all inputs. All makes sense, but for I makes things difficult, as is typically the case in computer science. Our insight is based on a simple but yet surprisingly difficult to obtain aha moment. That is, to relax program equivalence to only with respect to a single input I rather than all possible inputs. As highlighted here, now we got rid of the universal quantifier. It may not be super clear yet, but this insight and simple relaxation led to a series of powerful techniques to validate compilers and other related systems, inspire successful commercialization. Let's consider the example from earlier. It is a simple C program. We have a struct tiny with 3 character fields, C, D, and E. We have a function foo that takes a struct tiny x as its argument. If x.c or x.e not equal to 1, the function aborts. In the main function, we have a local struct tiny s with all its fields set to 1. We then feed s to foo. The code then returns. It is clear that above the boards should not be triggered, and the code should return normally. When we compile it using clan at -0, everything works correctly as expected. However, when we compile it at -01, the produced executable aborts with a core dump. Thus, we have a serious compiler bug, a miscompilation of wrong code. The bug turned out to be quite tricky to fix and took the developers a couple months to figure out the root cause and fix the bug. Now let's see how the relaxed definition of program equivalence, EMI, provides a powerful suite of techniques to find serious compiler bugs. Like the one we saw, it is probably not quite clear yet what is the connection. Now let's see. We assume a given program P and input I for program P. We profile the execution of P over the input I. We mark those executed statements as green and those not executed as red, and record output O. Then we mutate the program P by keeping the executed statements unchanged, but mutating the unexecuted or dead statements. For example, we can delete some of the dead statements, inject some, or both delete and inject. The only requirement is that the mutated programs should still compile. What interesting properties do these mutated programs have? As a matter of fact, they're all equivalent to the original program P with respect to the input I by construction. This should be quite clear, I believe, as we didn't change the executed statements. Now we can use the mutated programs to help find compiler bugs. If we produce a mutated program P prime and output of P prime on the same input I is different from the original output O, we have found a bug. And this is guaranteed, no false positives. Now let's see, how do we find the bug in clan that we saw earlier? Here is the original program P, which does not take any input. That is, it is a closed program. For this program, clan behaves correctly, both under -0 and -01, so the original program did not trigger the bug. We profile the execution of P, for example, using a coverage analysis tool such as GCOV. We notice that all the abort statements are not executed as expected, that is, they're dead. Thus, it is possible to produce a mutated program with some of the abort statements deleted, like this one shown on the slide. Interestingly, this mutated program now triggers a clan miscompilation under -01. Imagine that this mutated program is still very large. Typically, it will be helpful to shrink and simplify it before reporting it to the compiler developers. This process is called test input reduction or minimization. One may use tools like delta debugging, creduce, or Persis for this purpose. This is the one that was reported by us after test input reduction. You may wonder why Clan miscompiled this simple piece of code at -01. It turns out to be quite interesting. First, when calling the foo with the parameter s in the main function, optimization called GVN, global value numbering, decides that it's better to change the struct with 3 character loads into one 32-bit integer load. Turning 3 loads into 1 load sounds like a good thing to do. However, another compiler pass, SROA, scalar replacement of aggregates, notices that the 32-bit integer load reads past the struct's end because the struct has only 24 bits. Therefore, the compiler decides by mistake that the code has undefined behavior, although the original code does not have any undefined behavior. Once the compiler decides, whether correctly or incorrectly in this case, that a piece of code has undefined behaviors, it is free to do anything to the code. In this case, it decides to remove the 3 initializations. Recall that local variables in C and C++ are not initialized and may contain random values. Thus, it is possible for the C or the E field to not contain the value 1 and trigger the abort. EMI has led to a suite of effective techniques which have helped find a large number of critical bugs in both GCC and Clan LLVM and other commercial compilers. We have made GCC and LLVM a lot more reliable, and the effort is continuing. Correctness is well defined, and we have solid methods and tools. Thus, it's more or less tamed. Performance, on the other hand, is a totally different story. So, how do we pursue our dream of that perfect compiler? It seems an impossible pursuit. But despite this general impossibility, it benefits to consider this moonshot objective. In particular, I hope to advocate the following perspective. Let's systematically quantify how far our current compilers are from the perfect. Through this, we can identify the critical and profitable gaps and try to bridge them. In particular, although we do not have a perfect compiler, we can still have certain expectations of its behavior. As some initial steps, we have used several expectations to gauge the gap. Let's discuss some of such expectations. This is the figure we discussed earlier. A compiler has various transformations or passes which are informed by analysis and guided by heuristics. So what are these core expectations? First, heuristics play a crucial role in optimizing compilers. Therefore, we expect a perfect compiler to have optimal heuristics. Second, a perfect compiler should not miss any optimizations. For example, all constants will be folded, all dead code will be eliminated, and so on. Third, a perfect compiler's behavior should be monotonic. In particular, given more information, it is expected to do a better job, at least not worse. These are few examples that we have explored. There are certainly many, many more. We use these 3 expectations to guide our exploration. Next, let me briefly motivate them. First, perfect heuristics. The community has made significant efforts to improve heuristics used by compilers. But how good are they from the optimal? Does it make sense to spend more efforts doing this? If we could replace the current heuristics with perfect ones, we can answer such questions. This is precisely what we aim to do. Second, transformations. Decades of work aimed to improve compiler transformations analysis so they better optimize code. But how far is this optimization process from the perfect? How can we quantify this gap and identify what is missed? This is another challenge we aim to tackle. Third, compilers are expected to be monotonic. That is a core assumption in compiler research and development. That is, the more information a compiler has, the better code it should generate. A perfect compiler should certainly behave this way, but what about production compilers? This is the question we aim to answer. In the efforts I'll present, I'll highlight the conceptual, technical, and practical contributions with fresh perspectives, novel techniques, and practical relevant results. I'll now present the first piece on perfect heuristics. In particular, we focus on optimal function inlining from SPLASH' 2022. We were happy and grateful for the best paper recognition. There have been decades of work on improving inlining in compilers and inlining heuristics. However, none on the problem of optimal inlining and quantifying the window of opportunity. We took upon this challenge. So, what is inlining? It is a transformation that replaces function calls with the bodies of their callees. For example, we can inline the call to bar, resulting in the code on the right. Inlining expands the scope of many intra-procedural optimizations and analysis. Here, after inlining, we're able to infer now the if condition to be always false. Thus, after inlining, the compiler can easily eliminate the redundant if statement. And finally, fully simplify the code. On the other hand, overly aggressive inlining is bad, can lead to code duplication, as illustrated on this slide. Therefore, good inlining heuristics are important and need to balance such benefits and cost. With the right inlining choices, there is significant potential for improvement. Here we see the size reduction in the SPEC 2017 benchmark suite with inlining enabled versus disabled and up to 3 times improvement. This initial work focused on binary size because it's less noisy than performance measurement. First, as we saw, inlining is clearly an important transformation. Compilers use heuristic to decide which calls to inline. Our question is, how far are these from the optimal decisions to minimize binary size? To do this, we cannot naively try all combinations. The number of candidates is exponential in the number of calls. Any non-trivial program has a huge number of candidates. In this work, we show by carefully considering the structure of the search space, it is possible to drastically prune it and make the exhaustive search feasible for many more programs. I will not discuss the details here. It is a recursive partition of the call graph and leads to sound and drastic reduction from 2 to the hundreds down to 2 to the tens. Using our methodology, we can now measure the gap between the heuristic and the optimal. This plot shows the size increase due to heuristic inlining decisions from LLVM. The baseline is the optimal minimal size. The data set is based on the SPEC 2017 benchmark suite. We can see that in around half of the data points, the heuristic already achieves the minimal size. However, there are also cases with room for great improvement, the largest being almost 300% size increase. A quick summary of this work along the 3 dimensions perspectives. Are heuristics perfect? Technical, drastic search space reduction. Practical, optimal inlining data set for many applications. In fact, the same methodology could and should be systematically applied to other heuristics. The second work examines from the angle of perfect optimizations, also from SPLASH' 2022. We're grateful for Distinguished Artifact Award. It tackles the problem of detecting missed compiler optimizations. 2 difficult challenges. First, to determine what is possible to optimize. That is, what would the perfect compiler do? Second, to determine what our testing compiler has failed to optimize. Our insight for general and effective method is to use DCE, dead code elimination. So, what is DCE? It's the removal of code that cannot be executed or whose execution does not affect a program's behavior. In this example, the if statement body is dead, as the condition is always false. Therefore, it can be eliminated. The store A to 1 is also dead, as A is never read afterward. Thus, we can eliminate both. A perfect compiler will generate the code on the left, essentially return 0 in x86. However, real compilers fail at optimizing this simple piece of code. GCC generates code for the if statement and the dead store. Does LVM do better? It does not. In this work, we use whether dead code is missed to help detect diverse missed optimizations. But why do we care about DCE? What makes it interesting for our purpose? Our first insight is DCE is what we call an optimization sink. Removing dead code simplifies the remaining live code, which in turn makes analyzing and optimizing it easier. Therefore, compiler passes running after DCE have potentially a higher chance of doing their job. Compilers also try to repeatedly remove dead code. Thus, these passes also affect DCE quality. Also, there are other passes that DCE directly depends upon. Thus, a failure to eliminate a piece of dead code can be an indication of a failure in some other passes. In this work, we develop a method for making DCE failures easily observable. We can use DCE as a signal to detect these missed optimization opportunities. This is a quite simple and general insight, an idea which already inspired applications in other settings. But how can we detect that there is a piece of dead code in a binary? We can use multiple compilers to tackle this problem. Let's look at an example. Here, we see the control flow graph of the code generated by two compilers, namely LLVM and GCC. We can highlight which blocks of the graph correspond to which if statements. Doing so reveals that LLVM eliminated the first if statement. Therefore, GCC has missed an optimization opportunity. But how can we do this matching? The compiler's output is just a sequence of assembly. So we don't have, in fact, this correspondence. Our third insight is to make this detection trivial by massaging the input program. We insert something in the source code such that if it remains in assembly, we know that the corresponding basic block, for example, if statement, was not eliminated. We call these markers. Here, we implement them as function calls, and there are many other ways to implement this. Looking at GCC's output, we see that both markers have survived. But in LVM's output, only one remains. Therefore, we have detected a missed optimization in GCC. To quickly sum up, our length of dead code elimination is the following. Given an input program, we insert markers in all divergent control flow points. We compare the set of surviving markers from different compilers. If there is a difference, we have detected a missed optimization. In all examples, I use GCC and LVM as two compilers. But the method is flexible. We can compare different optimization levels of the same compiler, like GCC at -03 and 01, or different versions of the same compiler, like LVM 19 and 20, and so on. We can now answer the question of how good are compilers at DCE, and how do they compare against the ideal one that eliminates all dead code. We use a corpus of 10,000 programs generated by the random program generator CSmith. There are around 3 million dead blocks in these programs. A perfect compiler would remove all of them. But GCC and LVM at the highest optimization levels missed around 5% of these dead blocks. This demonstrates that there is room for improvement. As a benefit of this analysis, through analyzing different compilers and compiler versions, We also found and reported many missed optimizations in GCC and LLVM. A quick summary of this work along the 3 dimensions. Perspective, are optimizations perfect? Technical, DCE as a general lens or technique. Practical, many detected missed compiler optimizations. This next work focuses on the 3rd expectation, namely, to what extent are compilers behaving monotonically. It was presented at last year's PLDI. As users of compilers, we expect them to behave monotonically with respect to the information that they are given. That is, if the user provides more information or analysis such as value range is improved, we expect the generated binary to improve also, or at the very least, not becoming worse. Let's look at example. Here we have a function that compares 2 integers and another function bar that calls it. We can also see the x86 output. Imagine, as a programmer, we know some additional information that the compiler does not. For example, x is always greater than or equal to y. We can include it in the program via this annotation. The compiler can use this information to generate better code, as shown here. But do compilers always behave in this expected manner? Or can it happen that adding more information can result in worse binaries? Let's look at another example. This example contains more complex control flow, nested loops, and if statements. But as we can see, the compiler simplifies everything, doing a very good job. Because the outer if statement condition is always false, let's now try to do something like what we did before. We'll use the fact that argument in the h function call is always non-zero. We'll inject this information in the callee, again, using an attribute. Surprisingly, the compiler now generates way more code than before. Looking at the control flow graphs, clearly something has gone completely wrong. Our goal in this work is to find such cases automatically. Let's see how we do it. Starting with a seed program, for example, produced by a generator, we want to do the same thing as in the examples. That is to inject some information and test if the compiler is getting confused. We start by executing the candidate and observing its behavior. For example, what value do its variables take at various program locations, similar to our examples? Next, we inject this information back into the program. We use compiler built-ins. Again, like in the examples, the new program is semantically equivalent. Now we have 2 versions of the same program. We can compile both and use the oracle to decide if there is an interesting difference. If there is, we have detected an issue of non-monotonicity. If not, we can repeat the procedure. I'll now briefly explain the various steps in this pipeline. For the refinement step, we use compiler built-ins, as I mentioned. For dead branches, the built-in unreachable informs the compiler that the particular source location should never be reached. For value ranges, we use the same built-in, but guarded by the derived range. For example, we know V is between the lower bound and upper bound, therefore its negation is unreachable. The last step involves an oracle. We can use function markers as we did with DCE earlier. If a marker is eliminated from the original program, but not from the refined program, then the injected information has hindered the compiler. Using such a framework, we can now study the prevalence of this issue. We use, again, 10,000 sysmith programs. Our goal is to measure in what percentage of these programs are degraded given additional information. We see 9% degradation for LLVM and 17% for GCC. In total, we could trigger this behavior with around 20% of our test programs. And some of the degraded programs are common to both compilers. Clearly, production compilers can be very counterintuitive, and it is a challenge for our compiler community to make them more predictable. Using this end-to-end pipeline, we identified and reported quite some issues in GCC and LLVM. Most have been confirmed or fixed. The issues were related to a wide range of passes. For example, various analyses, peephole optimizations, and loop transformations, and so on. In this work, we measured to what extent a compiler is behaving monotonically. For reachability, namely, we use dead code and value range information. Our recent work at PLDI 2025 also has relevant results on alias analysis, but I will not discuss in detail here, and happy to chat about this later. A quick summary of this work along the 3 dimensions. Perspective, a compiler's monotonic, technical, introduces a fully automated detection pipeline. Practical, many detected misoptimizations. The 3 examined expectations: perfect heuristics, perfect optimizations, and perfect utilization of information. And a recap of the highlighted perspectives and the results. Toward that perfect compiler, these are some new but early steps. I believe this is a long yet fruitful journey to reimagine how to build compilers. The quick takeaways: compilers are foundational for trustworthy and performance software. It is a moonshot ambition for the community to build that perfect compiler. Our perspective is to understand the gap from the hypothetical perfect optimal compiler, and I discussed several efforts along this direction. I argue that the future compilers should have intelligent heuristics, be interactive, finding what is critical information and interacting with the user, or more powerful analysis, and perform both low-level and high-level domain-specific optimizations, so being a universal optimizer. Of course, there are many, many conceptual, technical, and practical challenges and hurdles. So, the dream is to build that ultimate optimizing compiler, turning the dragon into the super dragon. I cannot express how excited I am about this quest and direction. Thank you. I'm happy to take any questions now and discuss with folks later.
Okay. Thanks, Zhendong, and if there are any questions.
Hello, is it my, oh, great, it's on. Just a simple question. You had a table with bugs you reported and bugs that were fixed. What's the gap in between? Did other people fix it or just nobody fixed it?
That's from the EMI part, the earlier part.
Yeah, from the earlier part you had a table.
Yeah, with a couple thousand bugs, right?
Hmm.
Yeah, so maybe a bit more. So the numbers were from a year ago. First of all, the numbers should have been updated.
Yes. Yeah.
And now they're getting close to 3,000. And I think the bugs fixed also close to 2,000 also. And of course, there are some bugs which are very difficult to fix. And some bugs are, there's some duplicates as well, maybe reported by us, maybe also by some other teams as well, or maybe by the compiler developers themselves. And some bugs are not interesting to the compiler developers. And of course, inevitably, sometimes they also report some invalid bugs as well, because our misunderstanding of whether a piece of code has undefined behaviors or not. And that's a tricky issue. Yeah.
Thanks.
Thank you for that question.
Hi, Sam Westrick from NYU. You mentioned two ideas in the talk: optimality, often like optimal performance, and also predictability. And we want to understand what the compiler is doing. And these two, I think, can be in tension with each other. For example, as a performance engineer, I might want to understand what the actual code is that's running. But if we have an optimizer which is optimal, a small change to the input program might drastically affect the generated code and completely ruin any intuition I have about what code is actually running. So I was wondering if you could just say a little bit about that tension, this optimality, which is kind of not predictable, and yet this desire to have a predictable compiler.
Yeah, I think that's a great question, right? And although maybe I'll answer this with one bug from the security perspective, bug in quote, right? So I think as a developer who's very conscious about security, not to write secure code, and we're very, very careful. And sometimes compilers assume that the code, when compiles the program, has no undefined behaviors, may remove whatever you did for secure engineering, right? So that's also tricky. I think it's connected to what you said. And I don't really have good answers to that. And but again, a perfect compiler will be able to give us both, but in reality, not, right? And that's, I think, really a challenge for our community to think how to move forward, right? So I don't really have answers to this question. Yeah, thank you.
Thank you.
All right, maybe the other side.
Thanks for the great talk, Ben Titzer, Carnegie Mellon. So one dimension you didn't mention is compilation time. And so I often work on JIT compilers, and they have quite different designs. They might be a baseline compiler, there's no intermediate representation, or they might do speculation. I'm curious if you thought about applying some of your work to JIT compilers and what the issues are and what you might think are things that we could move forward with.
Yeah, Ben, yeah, thank you for that question. Yeah, so not from the performance side, not from the compilation side, but from using EMI, the method of EMI to test JIT compilers. We have done that. Some work published at the SOSP a couple years ago, how to find, I think, bugs in hotspot, in J9, and so on, right? Performance side, I really haven't thought too much about this, but happy to chat with you offline. Yeah.
Thanks.
Yeah.
Here.
Yes, my question is not so technical. It's rather I want to have your view on the intersection between the compiler research, compiler work in the LLM era. So one thing is, there is a tremendous important work on compilers for machine learning pipelines, but I'm more interested on your view in the other direction.
That's right.
So if the compilers of the future are these LLMs, and we have the Meta LLM compiler, and the authors of that paper published at GCC compare the quality by using the BLEU score, which is string comparison.
Right.
What's your view on this?
Yes,
What's the future?
Yeah,
What should we do? What compiler community should
Thank you for that question. I'll point to this particular word, intelligent. So for the part that I mentioned about optimal function inlining, now we have perfect data set. That is, for a call graph, what is the best inlining decision that we can use? Now we have this perfect data set, and we'll be able to use this, perhaps, train a machine learning model that to replace the heuristics within compilers. Inlining is one, and we can gradually replace all the heuristics by such models, perhaps. And that's what I call intelligent heuristics. Right? Yeah. So I hope that's an okay answer to your question.
Also, I think your methods that you have developed, or others in the community, about testing compilers should play a key role. When we have LLMs trained to play compilers, they need to be evaluated in a different way than they are evaluated today, because that community, I'm saying, has no idea about. I'm exaggerating, of course, but using a string comparison, string matching heuristic to value the qualities.
Yes, yeah. I think that's a very hard question, right? Because there is based on, one thing I did not mention, that for the EMI line of work, we focus on integer programs. I did not mention any thing about floating point. And in machine learning, floating point, that's really at the core, right? And so that means we have results that's different by a little bit. We don't know whether that's expected or not, right? So that makes it hard. But so I think maybe the biggest challenge is how can we develop very good, reliable oracles to tell whether something has gone wrong or not, right? Yeah.
Hi, thank you. Michael Koblenz, UC San Diego.
Yeah.
So I'm thinking about a lot of this work from the perspective of property-based testing. And it seems like a lot of what you've done is you've identified very clever properties, and then you cleverly produced generators, and then you found a bunch of bugs. And so I'm wondering what lessons we can draw about property-based testing. So, for example, do you typically find it's very hard to come up with a relevant property, but once you come up with a property, then you find a pile of bugs?
Yes.
Or possibly, actually, it's really easy to come up with a property, but most of the properties don't produce a lot of bugs.
Yeah.
And so I'm wondering what your insights
Yeah.
are about how to produce good properties,
Yeah.
how to
interesting
see
question.
which properties are good properties.
Yeah, very interesting question. So EMI is one property, right? It's actually a very simple property. It's easy to capture how to realize it. Makes, I think, make it powerful and also general to be able to detect a lot of it. It's actually a hyper property. And I know the recent work that people explored using property-based testing to find bugs in compilers, right, by capturing some expectations of what things should be. And I think that's interesting work, interesting direction. But again, it's always this balance, right? That is how easy it is to express the property, how powerful this can be used. And so, yeah. So I think it would be interesting, perhaps not treating the compilers as a black box. What we have been doing is treating compilers as black box. And I think in order to use property-based testing, we probably need to go inside to make it white box, right? To maybe to say, look at a particular like a transformation, then that will be clear, similar to translation validation, right? We can view that translation validation like Alive2, maybe as a very successful example of property-based testing. Yeah.
How dense is the space? Do you find when you come up with a property, you typically find a pile of bugs, or you typically find that property wasn't very good, we got to try a different property?
I guess EMI again is a very universal property, right? And the property-based testing work that I have mentioned is very. I mean, you have to think really hard to come up with very specific property locally, right? Perhaps even about the program that you want to test. For this particular program, what property you expect, right? So that's what I'm aware of.
Thank you.
But happy to chat with you also offline. Yeah.
I'd like to ask a question that's in the same general direction as the last one from this side of the room, thinking broadly about using machine learning and other approaches that can write code automatically. I wonder what you think about the prospects to move to a world where compiler passes just aren't written by people, they're found by search processes, maybe even search processes that have integrated formal verification, so that maybe counterintuitively, by leaning into AI, we could actually increase our assurance in the quality of the code while lowering the costs of building it.
Yeah. Adam, thank you for that question. That's a great question. And recently, during one of my PhD student defense, and Till, who did, I think, most of the work here, at least for the second part, and one of my colleagues from ETH, machine learning colleague, asked us, why don't you try to learn a full crack compiler fully automatically, right? It took us a long time try to argue and debate with the colleague that is hard, it's impossible. But I think he was not convinced, right? So maybe just adding that note here first. And I think if we do have a reliable oracle again to know whether the compiler is doing the right thing, and that's a big if. And if we have that, I think we can couple that with the AI technologies to be able to make compiler building, having heuristic is always easier because usually heuristic means any choice is fine, right? It's really just for the transformations and so on. And that's hard. So for that, we need a reliable oracle, right? Maybe, again, coupled with maybe a proof of the correctness of the transformations. Yeah? So I think that will be very fruitful, and but there are some really hard challenges we have to think about. Yeah.
Thank you.
Leo Marker, Jane Street. Looking at the how point on this slide, you talked about heuristics, you talked about optimization. I think this is the first time that I'm seeing interactive design. I don't think you talked much about that. Could you say a few words about what you mean by that?
Yeah, that's right. So it's more related to the recent work that my student Michel Weber has done, is on understanding alias analysis impact on compiler optimizations at this year's PLDI. And what we found is, for the spec benchmarks, if you remove alias analysis totally, the impact was minimal. But there's a small percentage of these alias queries are supercritical. So then the question becomes, how can we identify this small percentage of information that is critical for compiler optimizations? And then try to get this information maybe by interacting with the user, or maybe try to improve our analysis, right? So maybe that's, I think, one way to look at it. But in general, beyond alias analysis, I think that's true as well, right? So that is, how do we figure out the most critical questions that will make compilers do a much, much better job? Let's not try to build maybe a fancy analysis. Let's try to ask the user, is this true or is not true? Right? Maybe they are just to follow upon this. And I know we have a lot of colleagues here who work on formal verification and so on. But imagine a piece of code that has been formally verified. We put so much effort. We have the specs. Why don't we try to have this information not just thrown away by the compiler, but being leveraged by the compiler? I think that would be very, very nice to have.
All right, from this side.
Hi, so my question is kind of the opposite of the property testing one. So you've shown us 3 example results, which started from, let's examine if a given optimization method is implemented correctly or optimally by these compilers. And I wonder if you can go even more black box, and what if I just have a program that I know is not compiled into something that is as efficient as I would expect it to be, but I have absolutely no idea which optimizations are the ones that are at fault there. So okay. in that case, so can you go even more black box? Can you start from, oh, I don't know, because this is not fully black box, right? You still make assumptions about, okay, these are the optimizations that happen inside the compiler.
Yeah, thank you for that question. Let me try to answer that based on my understanding of your question. And perhaps what you are thinking is, well, I put this very vaguely as a universal optimizer. That is, usually when we teach compilers to our students, we say, you should think really hard about the data structures and algorithms, and then pick the right data structure, pick the right algorithms, and then give the job to the compiler. But I will argue that's not. Let's try to, maybe as you said, right? One step back, and we try to ask the compilers to do even more, to be able to discover these kind of high-level deficiencies in our code and try to optimize it.
No, I mean, I meant more like you don't, the compiler internals are the ones that you wouldn't make any assumptions about. Like, what if you don't know that, oh, this program is compiled into something inefficient because that code elimination doesn't fire correctly, or, oh, because the inlining is not optimal. You just, all you see is that, okay, there's this program, there's a reasonable, like in my head, I have a reasonable way that it could be compiled efficiently, but yet what comes out of the compiler is not efficient, but I have no idea which transformations in between are at fault.
I see. Yeah. I think a lot of times we as developers already maybe try to do that, right? Try to work around or together with the compiler, right? And I guess as you suggest, maybe we should think more, right? How to be able to tell, suppose we have expectation. Yeah, usually I mean, we can do we do a lot of profiling already, right? Profiling gives us a lot of information to see whether there's anything surprising can guide us, right? Yeah, but I think I see your point, and I think it's an interesting direction to think more. Yeah. Thank you for that question.
Maybe the last question.
John, yeah.
So John Hughes from Chalmers. I have a question about your dead code elimination. So you wanted to have ground truth to compare against, and you obtained that by saying if a piece of code is eliminated by any compiler, then it's dead. But that, of course, is an under-approximation of the real dead code. Yes. However, if you were to take the generated programs and then test them, then code that is executed is definitely not dead. Yeah. And by doing that, you could get an over-approximation of the set of dead code. Okay. And you can imagine that maybe if you used a good concolic testing tool, something that aims to improve coverage of the tested program, you might be able to get a test suite which reaches almost all the non-dead code. Okay. That might give you an overestimate to compare against. Have you considered using that?
Okay, yeah, John, yeah. Thank you for that question. First of all, let me clarify before I answer your question that for the study we did, we used C-Smith generated random programs, and these programs don't take any inputs, which means the runtime gave us the perfect information. Right, so that's the optimal. We compare against that optimal.
Okay.
I just want to clarify that aspect.
You talked about looking at the dead code detected by different compilers and comparing that.
Yes, right. So that's in practice. Of course, like by running the runtime information, give us the perfect information, right? To tell us which blocks are dead, which blocks are not. We use that as a reference. But for bug finding in practice, it's because the production compilers are now close to that perfect compiler. So we want to focus on those interesting bugs. So that's where we say, oh, if GCC is able to do this, but LLVM cannot, then that's perhaps more interesting. Or vice versa. If -03 GCC can do it, but -01 was able to eliminate a block, but -03 couldn't. That's a surprise. So mainly it's for programmatics.
Okay, thank you.
Okay, yeah.
All right, so this concludes the keynote session. Let's thank Zhendong again for the wonderful talk.